So speed and velocity are different things. Right? So speed is a measure of how fast you're going, similar to velocity, but speed does not indicate direction. That's why when you're driving a car, or someone else is driving a car, and you look at the speedometer, it tells you the speed, not the velocity, because it does not indicate direction. Right? So speed is what's called a scalar quantity. Right? So scalar is kind of the counterpart, we'll use that word, for, to vector, right? So scalar is a quantity that only has magnitude. It does not have direction, all right? Sometimes speed and velocity can have, the magnitude of velocity, meaning just the value of velocity without direction, can be the same as the speed, though it may not always be the case. All right. So just think in your head, they're different things, though they're similar, because they're both a measure of how fast something goes. Right. So typically when you're dealing with speed is distance traveled divided by time. Right. So distance rather than displacement. So let's just focus for the rest of this lesson on constant velocity motion, right? So constant velocity motion means that whatever object we're analyzing is moving with a constant velocity, constant meaning the same. So its velocity is a certain value, and it's that value forever, or at least for the time we're analyzing the object. Right? So another way you can kind of think of this is that for every unit of time, for every equal unit of time, I should say, the object travels the same displacement. So every equal interval of time is really what I should say. The object travels the same displacement. So remember, that does include direction. All right, so this GIF here kind of shows an object, a block here, moving in a straight line with a constant velocity. All right, it's moving to the right at some rate of change of displacement. We can compute that if we wanted to, but let's move on. We have some more interesting examples. Right? So there's different ways we can model constant velocity motion. The first of which is called a motion diagram. Right? So I'm not going to talk too much about motion diagrams, but they're kind of an easy way to depict the motion of an object. Right? So for example, here I've got a turtle that's traveling 10 centimeters per second to the right. But if I'm trying to draw this on a piece of paper, drawing a turtle moving can be kind of difficult, right? Since, this isn't Harry Potter, we don't have moving pictures that we can just write on paper. So here, this turtle, right, we can kind of represent the turtle as a dot, since dots are a lot easier to draw than turtles, and for equal intervals in time, draw a dot of where its position is, where its location is. Right? So this turtle, since it's moving at a constant velocity, let's draw a dot for it every 1 second. So since it's moving at 10 centimeters per second, that means after 1 second it moves 10 centimeters, after another second it moves another 10 centimeters, so on and so forth, leaving us with this dot diagram that has equal spaces in between. And that's because our turtle travels the same distance in that same amount of time. Right? So dot diagrams are kind of a very simple, easy, quick way to kind of picture and diagram what's going on, kind of model. All right, so another way we can model constant velocity is by graphing. All right, so we're just going to look at one specific type of graph now. We'll kind of evolve our knowledge later to include different types of graphs. But first, we're going to look at position versus time. So remember, when we're dealing with something versus something else type of graph, whatever's the before the verses, that's our vertical axis. Whatever's after the verses is our horizontal axis. Right? So here we're graphing position as a function of time. Right? So what that basically means, if I were to write an equation for position, it'd be dependent on the time, which, seems reasonable. And we'll kind of get more into equations next lesson, right? Or maybe the lesson after that. We'll see. So here we have kind of a depiction, kind of in live action, of a position versus time graph, right? So here we have a blue car and a red car that are both traveling. Right, so we see here the car starts at a location of 20 meters, hence why our graph starts at a vertical location here on our y-axis, so to speak, at a position of 20. And that car is traveling at a constant speed, constant velocity, rightwards. And we see here that the rate of change of its displacement is smaller than that of the red car. Right? The red car starts at 0, but it doesn't start moving until 4 seconds after the blue car starts moving. Right? So these graphs kind of here show this. And if we were to measure, time, we would see that the moment in which they're both at the same position is at the 7-second mark. Right? So you kind of see that right there. And you see that's where their graphs intersect. Right? So these graphs can be very interesting and useful to kind of look at, right? So kind of the simplest thing you can analyze and interpret here from a position versus time graph is the location of the object at a certain time. Pretty straightforward. But something else we can learn from these graphs, which is not as obvious at first glance, is we can actually find the velocity of the object based on the graph. Right? So we see here these lines have a constant slope. So if we remember, right, we said that velocity is the rate of change of position over time in a certain direction, right? So displacement over time. Right? So let me go to somewhere I can write. Hold on. We said velocity is equal to displacement over time. Let me just write that literally in words. Displacement divided by time. Well, our graph was position versus time, right? So in kind of the terminology we're used to, if we're finding the slope of a position versus time graph, well, slope we can compute by, it's our change in y coordinates divided by our change in x coordinates. Do you remember that from math class? So it's rise over run. Right? So if our change in our y coordinates here is my vertical axis, which is position, so that's going to be our change in x, divided by our change in run, so our time, delta t. Hold on a second. Our slope has the formula delta x over delta t. That's velocity. So the slope of a position versus time graph tells us velocity, which is very useful. Very useful indeed. All right, so let's look at an example of computing average velocity. All right. So we have a person here that runs 50 meters in a straight line at 5 meters per second. The runner then continues to move in that same direction, but then now goes from running to jogging at 2 meters per second for another 50 meters. And then the person turns around and walks at 0.8 meters per second back to where the runner began. Right? So we want to calculate the time spent running, jogging, and walking. All right, so I just want to sketch this kind of quickly to kind of depict what's going on. So we have a person here, and that person, let's say, starts at 0 meters. So that's their initial position. So that's where to define our origin. And let's define rightwards as our positive x direction. All right, so our person runs to the location of 50 meters. All right, so here's our person at some amount of time later, which we're supposed to compute. And during that time, they're moving at 5 meters per second. And then they travel another 50 meters, so a little mental math. We know that their location then will be at 100 meters. All right. And they're doing that at a jog, and they're doing that at 2 meters per second. And then the problem tells us they return back to the origin, right? So that's going to be difficult to kind of draw, but if they started here, then they go all the way back here to the original spot, traveling now in our leftward direction. So if you write the velocity, it's negative 0.8 meters per second. So that's kind of depicting what's going on. So we want to find the time that it takes to do all the intermediary steps here. All right, so we can find the time it takes while running, jogging, and walking kind of a variety of different ways. One could be just thinking about it. So for example, the running section, they're traveling 5 meters per second. Well, that means after 1 second, they're at the 5-meter location. After another second, they're at the 10-meter location. 3 seconds, they're at 15 meters, so on and so forth. We see that it takes 10 seconds to get to the 50-minute mark, right? Another way we could look at it is essentially we're seeing, well, if they're traveling 50 meters, if we divide by 5 meters per second, which is really what we're doing there, we end up with 10, and looking at units, meters cancels, and we're left with 1 divided by seconds in our denominator, which, doing a little math, gives us just seconds, all right? So 10 seconds running. All right, so we can do a similar thing here. We travel 50 meters at 2 meters per second when jogging. So 50 divided by 2 gives us 25 seconds jogging. Sorry, my handwriting on the screen's a little messy, or I should say messier than normal. And our final one is actually, if we want to be a little careful about it, it's a displacement here of a negative 100 meters divided by our negative 0.8 meters per second, giving us 125 seconds. Right? So that's the time it takes to run, jog, and walk. So now the problem asks us to calculate the average velocity for excuse me, the run and jog together, the jog and walk together, and the run, jog, and walk all together. All right, so here we can use the equation we learned for average velocity. So if we want to find the average velocity for the run and jog together, all right, so that's basically kind of this first region here that's depicted. So we know the average velocity is change in position over change in time. So that's our final position minus our initial position divided by the amount of time that's elapsed. All right? So our final position, that's going to be at the 100-meter mark. That's when we're done jogging. Minus our initial position, that's the beginning of the run. That's what we called 0. Divided by the total time that's elapsed. So that's going to be our 10 seconds plus the 25 seconds, giving us 35 seconds. So computing that and rounding to 2 significant figures originally presented to us in the problem gives us 2.9 meters per second. And the number we got here was positive, meaning our velocity is in the positive x direction, right? So if we want to kind of describe this in words, this velocity is 2.9 meters per second in the direction of our initial motion, in the direction of our initial run. So the next part asks for the jog and walk together, right? So the walk ends at a location of 0 meters, and the run started at a location of positive 50 meters, divided by the total times elapsed. All right, and our total time elapsed is going to be 125 seconds plus the 25 seconds, giving us 150 seconds. All right, so this gives us a value that's going to be negative because our numerator is negative. So negative 50 divided by 150, that's negative 1/3, but our answer is not exactly 1/3 because that would be an infinite number of sig figs. So we have to approximate this as a decimal with 2 significant figures. So 0.33 meters per second. Our answer here is negative, meaning that our average velocity is leftward, which is reasonable, and also the velocity value we got is less in terms of speed compared to the 0.8 meters per second leftward, which also makes sense because we have a chunk of time which we have rightward motion. Oh, and it looks like we've run out of time. So the last part of this example will be done in the next video, which should be pretty short.